Hello, I'm Emery Hill. I'll be presenting my magnetic molasses lab. So to start with our introduction, the purpose was to collect data of a magnet falling through a tube of aluminum foil and then to model that situation and then compare the computational predictions with our observed data. For a sneak peek at the results, the real time was 0.75 seconds, the estimated time was 0.487 seconds, and that can be explained through some of the physics. We get into that. So with some, we got to recognize some of the physics formulas and principles at work here. So we have Faraday's law. It's pretty important for this lab. It's kind of the basis of it all, relating electric potential, electric fields, magnetic flux, and it kind of is also uh, related to all the other Maxwell's equations, right? And then I thought it would be good to add in here. We have the force of moving point charges, the magnetic force, and then the magnetic field. Both of these are required as well. And then GlowScript was used to create the model. That's a picture of the visualization on the right there, the blue being the magnet inside, and the gray being the tube of aluminum foil. For the system surroundings and initial conditions, the image is a little bit blurry and the magnet is actually inside the tube at this point, but the system is the magnet, it's inside the tube, and the surroundings are the foil, air, ground, everything else. And for the initial conditions, time started at 0 seconds and the magnet started with 0 velocity. So for the procedure, this is just a little bit of the code over here on the right. Nothing specific right now, but um, first we measured the time it took for the magnet to fall through the tube and took measurements of the tube itself. And then I coded the computational model to estimate the time, and we'll get into that on the next slide. And then obviously I also add visualization code so that we can actually see what's happening. And then comparing, the last step is just to compare the times. So here's the code. In the yellow there, that's the geometry of the tube. Everything that's not colored is skeleton code. The red is the initial conditions that we talked about. The purple ones are different functions. We have the flux and uh, dipole. So that's our functions for those. The green is the while loop, the simulation while loop, and then the blue is everything we did to uh, basically have forces acting on that magnet. It's all of the force elements of the code. So to look at the main results here, um, the as I said before, the time was 0.487 seconds. Um, and again, you saw this image here, but this is it with the graph. This is a graph of the time. And as you can see, it flattens out in the middle because that's when the magnetic force is the strongest. So basically it's slowing down the most at that point. And then kind of at the end, it drops off again because the force kind of diminishes at the very bottom. But yeah, the velocity slows down the whole time because there's a force acting on it. Right. And the difference in the times we can get into in a second. So with our analysis and conclusion, um, the predictive value was 0.487 seconds, like I said, and the real time was 0.75. So the difference here is likely due to imperfect conditions. There's a pretty big gap in this lab, because if the magnet, which I know it didn't, if it doesn't slide perfectly down the center, it can hit the edges, which can change its velocity and just that adds friction force as well. I think that's probably one of the biggest issues because the magnet did, I think, scrape the sides of it. And then air resistance was ignored. I don't think air resistance would do too much, but it still can have a contribution. And all of these combined could account for the, 0.25-ish seconds uh, that were difference. But besides that, everything uh, is accurate and the shape of the line matches the conceptual knowledge of the situation, right? So for some final questions, if the resistivity of the conductor were reduced, basically the current would increase, magnetic field would increase, the magnet would fall slower. And if there were holes or slots cut in the tube, current would decrease, magnetic field decreases, and the magnet would fall faster. For some potential errors, timing inaccuracy, if the time wasn't measured perfectly, that could cause issues. Measurement error, like the geometry, any of that, that can also cause issues in the lab if anything was measured inaccurately. I guess that kind of goes along with time. And then friction in the tube, like I mentioned, that can have forces that we don't want, which can also be an issue. Thank you.